45 seconds. The sky is a hard, pale blue, but the air feels wired, like a room before a breaker trips. Sirens braid with a low thrum, and somewhere a dog refuses to bark. Above the horizon, a bright grain has hardened into a streak, then into a wound of white fire. It is not a star, and it is not slowing. The object's path is locked, gravity's rails set long before tonight, and there is no launch window left to nudge it aside. This is what the final half-minute looks like: heat blooming, glass trembling, a breath held by an entire coast. The question is not where to run. It is how we arrived here at all. We rewind. The drama began long before the countdown, with quiet frames from survey telescopes scanning for near-Earth objects. They look for a faint dot that shifts against the star field, then confirm it on later passes to solve for an orbit. But many space rocks wear black coats, absorbing light like charcoal. Some arrive from the sunward glare, where ground observatories cannot stare. Clouds roll in, the moon brightens the sky, and daytime simply erases our view. The result is a sky full of hiding places. Even with a detection, certainty is earned slowly. Early measurements draw a wide cone of possibilities, not a single line. Each night of tracking narrows the corridor and updates the odds. If the cadence breaks, the corridor stays wide and the warning shrinks. That is how a harmless speck can become a threat in what feels like an instant. Surprise is not magic. It is the sum of dark surfaces, bad angles, imperfect weather, and the stubborn math of orbits meeting Earth. A global net of wide-field telescopes sweeps the sky each clear night, taking repeat images and asking a simple question: what tiny point moved? Software subtracts last night's stars from tonight's frame, flags a wandering speck, and links detections across hours and across observatories. With each time-stamped position, astronomers fit an early orbit and estimate size from brightness and reflectivity. Radar, when geometry allows, paints the target with radio and returns a sharper range and speed. Separate stations add parallax, tightening the track. What begins as a rumor of motion becomes a path through space, described not as a single line, but as a cloud of possibilities that narrows with every new look. From that first ping, an alert lives through a disciplined loop: discovery, follow-up, confirmation, risk release. Nightly cadence matters. Miss a night, and the cloud of possibilities widens. Teams publish updated odds, and civil agencies rehearse what those odds would mean on the ground. To shrink the blind spots near the sun, engineers are building space-based sentinels that watch in infrared, where dark, charcoal worlds glow with heat. Those eyes can see during the day, above weather and moonlight, turning surprise into schedule and giving small nudges the long runway they require. An orbit is an ellipse with a closest point to the Sun, the perihelion, and a farthest point, the aphelion. Where that ellipse crosses Earth's path are the orbital nodes, the only places a collision can truly happen. An impact requires both bodies to arrive at a node at nearly the same moment, inside a narrow impact window measured in minutes to hours. Most passes miss by vast distances because the timing is off by a little. But timing shifts each year as gravity from planets and sunlight's gentle push tweak the path, sliding that window back and forth across the calendar. During a close flyby, a small corridor in space called a gravitational keyhole can redirect the object just enough that, on a later return, a resonant alignment places it back at the node at exactly the wrong time. The difference between knowing years ahead and days ahead is everything. With years, a nudge of millimeters per second compounds into thousands of kilometers of missed distance. With days, only brute force remains, and even that may not be safe. Early knowledge buys leverage. Late knowledge buys sirens. An asteroid does not simply fall, it slams into a fluid wall. At a steep or shallow angle, it meets air that cannot get out of the way fast enough. The gas ahead compresses and heats, piling up as a bow shock. Dynamic pressure climbs until rock glows, surface minerals vaporize, and a sheath of plasma blooms around the body. Even strong stone cannot ignore physics forever. If the ram pressure exceeds its strength, the intruder bursts, releasing energy as a blossom of white fire. This airburst can occur high above a city, bright enough to cast moving shadows at noon, hot enough to singe rooftops, violent enough to rattle ribs. The light comes first, sharp and silent. The sound is still on its way. Fragmentation turns one threat into many, but not always in our favor. Shattered pieces continue along nearly the same path, each wrapped in its own shock and wake of incandescent gas. Some melt and flare out, others survive to lower altitudes where the air is thicker and the hammer blows harder. The combined shock front outruns the wind and arrives as a wall of pressure that snaps branches and showers buildings with broken glass. Windows fail not from heat, but from the sudden jump in air, and injuries follow the shards. Seconds may pass between the flash and the boom, a quiet that tempts people toward the window. The safest act is simple and unspectacular. Step away from glass, cover eyes and ears, and let the shock roll through. A rock the size of a house, around 20 meters across, is a bruiser of the sky. It usually breaks high, a fierce airburst that turns morning into welder's daylight, then slams a pressure wave across a city. Most injuries come from shattered windows and flying glass, not from craters. Step up to around 140 meters, and the story changes from broken panes to broken blocks. That mass can deliver a region-scale disaster, widespread blast damage, fire ignitions, and, if it hits water, a basin-wide surge that races toward coasts. Cross the line to at least 1 kilometer, and you are speaking the language of continents. Dust and sulfate loft into the stratosphere, sunlight dims, temperatures fall, harvests fail, and ecosystems stagger. History keeps the cautionary ledger. Tunguska leveled forests without leaving a classic crater, proof that air can be a weapon when rock arrives fast enough. Chicxulub carved a wound in the Yucatan and, more crucially, filled the air and oceans with the ingredients of collapse. Where an impact happens, steers the outcome. Land strikes mean firestorms and shock through bedrock. Deep ocean strikes couple energy into long-period waves. Ice sheet strikes can inject meltwater and debris into currents and skies. Angle and speed decide how much energy couples to air versus ground. In every scenario, size sets the ceiling, but location and geometry write the fine print of our day after. The aftermath of an impact unfolds in layers, each wave slower but broader than the last. First comes the flash, a pulse of thermal radiation that can ignite dry fields and blind anyone who looks toward it. The shock wave follows, shattering glass, collapsing roofs, and throwing debris outward like invisible shrapnel. Fragments of the object and pieces of the ground it struck arc through the air as molten projectiles, falling back in a fiery rain. These are the first seconds of chaos, defined by light, heat, and pressure. Then the world begins to breathe through dust. Fires feed on oxygen and release plumes that merge with the vaporized soil and aerosols lofted into the stratosphere. Power grids fail, communication lines collapse, and rainfall may turn acidic near the site. In the following months, a veil of soot can drift across hemispheres, cooling some regions while others burn. Crops fail, migration begins, and supply networks fracture under the weight of scarcity. The common mistake is to imagine the crater as the only wound. The true damage spreads through air, ocean, and climate, a slow echo that keeps answering long after the impact itself has gone silent. Changing fate begins years, not days, before a threat. The most elegant tool is a kinetic impactor, a spacecraft that rams the asteroid and steals a whisper of its speed. A tiny nudge, given early, grows into a wide miss by the time orbits meet. When the clock is tighter, planners consider a nuclear standoff, detonated at a distance so that intense heat boils away a skin of rock and the recoil nudges the mass. It is not about blowing it to gravel. It is about sculpting momentum. Radar, light curves, and sample returns feed the models that tell us how hard, from what angle, and for how long to push. For patient timelines, there is the gravity tractor, or an ion tug. Park a heavy craft beside the rock and let steady thrust or mutual gravity pull it onto a safer track. If breaking the object is unavoidable, fragmentation must be controlled so pieces are small enough to burn high and not big enough to seed a shotgun of strikes. Every option depends on knowledge and time. We need to know the composition, spin, and structure, and we need warning long before the last orbit. That is the core rule of planetary defense. Detection buys decision space. Decision space buys delta in trajectory. And that small delta keeps a world out of harm's way. Right now, we have more eyes on the sky than at any time in history. Wide field surveys stitch the night into a moving map, radar sharpens range and speed, and follow-up teams turn faint rumors into reliable tracks. A recent demonstration showed that a deliberate shove can change an asteroid's path, and the measurements that followed taught us how mass, spin, and rubble behave under a blow. The next step is simple but ambitious. Place infrared sentinels in space, above weather and daylight, where dark, carbon-rich rocks glow with heat. With those watchers, surprise shrinks, warning grows, and every quiet night buys us decision time. So we circle back to the last 45 seconds. The sirens, the tremor in the glass, the bright wound across the sky are not where fate is decided. Fate is decided years earlier, in budgets approved, instruments launched, drills rehearsed, and public trust earned. If warning comes late, the best actions are modest and life-saving. Step away from windows, protect your sight, follow official guidance, move inland if the strike is at sea. If warning comes early, small nudges become a safe miss, and the countdown never starts. If you want us to always have more than 45 seconds, support the science that watches the dark.